Welcome back to linear algebra. Let's jump in hockey. What is an invertible matrix and what is another name for such matrix? An invertible matrix is a square matrix. In which another matrix exists that it commutes with and that their product is I. Another name for that matrix is non-singular. What are the coefficient matrix and augmented matrix of a linear system AX equals B? The coefficient matrix is A, the augmented matrix is A partitioned with B. Assuming that A and B have opposite or appropriate sizes, how might you compute the jth column vector and the ith row vector of AB without computing the entire product? Jth column vector? Okay. The jth column vector, you're going to take the jth column of I'm assuming it's A times B, and now I'm gonna say my gut says if it wasn't structured this way I would say a different way, but no, I would no, I'm ignoring structure. Jth column vector of B, or A times the jth column vector of B, and the ith row vector of A times B. Yep. As a matrix is a rectangular array of numbers. What is a row column vector rule? What is the row column vector rule for computing AB sub ij? Row column rule. The first row of A times the first row of B plus the second row of A times the second column of B plus dot 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 plus the last row of A times the last column of B. Multiply row I of A by column J of B and sum the products. Oh my gosh. Okay, yeah, I totally missed that. But I know how to do that, but the row column rule, that terminology kind of threw me off. All right. Okay, that's great, I guess, what we did yesterday. All right, I'll be back in a second. All right, I got that question right now. I'm gonna go ahead and continue doing more practice problems. All right, so I finished the first pass of 1.7 and started the second pass. Last question for first pass was, if K times A is symmetric and K does not equal 0, does that mean A is symmetric? I think yes. Just if you look at, like, for example, you don't need to look at the main diagonal. That doesn't matter for symmetric. You're going to look at the entries mirrored over the main diagonal. And for example, in a 2x2, it's just going to be like these two numbers equal each other. And so if we just divide both sides by K, like I guess the way you could say it is the number, to be symmetric, the numbers mirrored over the main diagonal have to be equal, and if you divide K, a constant, from both sides, the ratio, they're still going to be equal. You're doing the same thing to both sides, so. Then I start the second pass. If this upper triangular, lower triangular diagonal, and first of all, lower triangular, because there's above the upper main diagonal is all zeros. Is it invertible? I say non-invertible. I'm not exactly sure on this. I know for diagonal matrices, it has to be all non-zeros in the main diagonal, and I think that's the same for triangular matrices. I don't know if that's for all matrices for determining if it's invertible from inspection, but I know it is for diagonals. I'm somewhat sure it is for, confident it is for triangular matrices. Uncertain, but it's possible that it's for all matrices. Probably not, though. Next question was finding a squared, a to the set -2, and a to the -k. Since it's a diagonal matrix, you just apply the exponent, or the matrix, the power of the matrix to each of the entries. So that's good. And then this was basically, it was like this this was like to the 1000th, and this was to the -1000th or something. Is that just an exponent question? What number is this? 14? Oh. Oh. Yeah, it was this to the 1000th power, but I think since it's this diagonal matrix, you just apply that power to each of the entries. 20 was another one of determining if it's invertible based off of inspection alone. Again, same thing with that, all non-zeros in the main diagonal to be invertible. If it's triangular or diagonal, what is this? This is a symmetric matrix. Determine like values of A, B, and C so that this is symmetric. And so I went ahead, since this is linear algebra, let's make a matrix, augmented matrix, and then solve for that. And I'm not quite done with it yet, so that's what I'll be working on starting tomorrow. So that's it for today. Talk to you tomorrow. See you.